I think you might have come over here for this talk because at some point in your life you bought yourself Amazon Echo or Google Home, or just played with Google Assistant or with Siri, or just watched Google I/O keynote from 2 days ago where they announced Google Duplex. And you start to scratch your head what this voice user interface is about. So if that's the reason, this might be the talk for you. Because what I would like to do is I would like to drill down together with you from a position where we just said something to a place where computer actually understand what we've said. And I've been doing voice user interfaces as an applications for quite a few years, and quite many years ago. And when voice interfaces became very popular, not in the banks where you had the IVRs and you called in and somebody said, yes, if you want to your credit account, say 1 or press 1, which was hilarious. But to a place where we could actually open a refrigerator and say, Alexa, please order some eggs. And the computer will do it. So we'll try to maybe demystify that, or just try to understand. Because whenever we come across voice user interfaces in public, or on YouTube, or how people use it, what we see is mostly something like this.
Simon says, hey Google, repeat that.
Hey Google, repeat that.
Alexa, Simon says, hey Google, repeat that.
Hey Google, repeat that.
And we can go that infinitely.
Alexa.
So what I'll try to do is I'll try to get the voice user interface in such a way that your manager will get it. So let's get started. Whenever we talk, especially at IT conference, we should start with a kind of an architecture. So we can say voice user applications or voice user interface or voice user recognition has its architecture. And we can show a very classic example of an architecture, something coined by Ted Noward. Every system can be explained with 2 boxes and a cylinder. So we have a speech that goes in and some magic happens, and we get some result. We will go a little bit beyond that, though a disclaimer at the beginning, things I will be telling you is kind of a naive implementation of speech recognition. You can go back and take it directly to code, and it will work, but for sure you won't be getting as good result as Google is getting or as Apple with Siri is getting. This is a very naive way of understanding what's happening behind the what's happening under the hood. So when you got your iPhone and you press the button for Siri to tell something to your phone, what happens? There are multiple steps, and we'll be going through them one by another. Whenever we go through the speech recognition, we have to undergo some multiple steps. The way they are called here is the classic approach, the way they are called in the papers and in computer science. So we do the endpointing. So we try to figure out when the speech actually happens and when somebody stopped talking. Then we do the feature extraction. So we try to get from the audio stream to some features that allows us to distinguish between, let's say, so-called letters in spoken language. And then we get the actual recognition. And we get when we got a word or a sentence that was recognized, we will have to go through the natural language understanding. So to make the computer actually understand what we meant and what we are thinking, what we are trying to say. And when we got all those bits and pieces, we can manage the dialogue. So we can manage how the conversation is progressed and how the conversation is being how the conversation turns down. We'll walk through this one by another. So we start with the first thing. We remove the silence. So we have an audio signal, we have an audio waveform, and we need to figure out when somebody actually says something, and when it's just a noise, an ambient noise, or humbling, or silence. So if we have a audio signal or a wave file, that's this kind of typical what you get when you look from people talking to a computer. We can distinguish three important parts. We have a silence beat, so nobody was saying anything whatsoever. Then we have something called unvoiced, which is not yet a spoken thing, but when we are preparing ourselves to say a word, our vocal tracts, so our vocal tracts start working. Because, for example, if we say a letter B, or if we say a letter P, we accumulate a bit of air in the mouth to bring the pressure to say B. And this sound, and our throat, our vocal tracts already start making some sounds. They are totally not heard, but they can be reflected already on the audio wave. And then we have the actual voice. So we have a voiced signal, and that's something we will be trying to focus on. So before we even start getting to the recognizer, we have to remove everything that's not relevant. So we have to remove the silence. And as we know, this is an analog signal, so there is no concept of silence. There is this ambient noise, all the noises from the background, all those different things happening while you talk or while you speak. So we have to undergo some filtering. They can be more or less sophisticated. This gets pretty neat, but we can imagine that it's kind of measuring the amplitude of the wave, figuring out the smallest amplitude, and setting up a kind of a threshold to remove everything that goes below the threshold. The thing is that if we have an audio like this, it's pretty easy. But when we are doing it live with Alexa or Google Home or with Siri, we have a constant kind of a live stream of audio, and we have to figure out where the person actually stops saying anything. Because when somebody starts saying, it's easy in most of the cases. You say Alexa, and it wakes up, and then Alexa starts listening. When you press the button for Siri, that's an indication that you will be talking. So that's the starting point. But when it comes to the end of the speech, you have to wait a bit to figure out whether somebody stopped talking, or whether he or she will continue. If you ever played with Siri, you might have noticed something like this: that you press the button, you say, Siri was on my calendar today, but you are doing it in a noisy environment, and Siri keeps listening and keeps listening and keeps listening, and after some time it just decides, okay, I think he's done or she is done, and stops listening. So what can be the threshold, the minimum, the limits of listening when it comes to speech? There is some research going on. Well, there has been some research conducted back in the 90s, which sets up on some work from psychologists from late 60s. We can distinguish three important limits when it comes to response time. So how fastly or how quickly computer responds, and this can be used not only in voice interactions, but also on all kind of a website and so on and so forth. So if we have a response time slightly less or around 100 milliseconds, the human perception is that the computer, the system reacts instantaneously. So there is no lag whatsoever. When we get to a point of about a second, there's no feedback necessary. So human still perceives the system working, that is working. But a person can lose kind of a kind of feeling that it's operating directly on system. There's kind of a latency, and that indicates, for example, how long we should be listening before we get to a point that we stop recording and start recognition. In this work, because this is coming from Nielsen-Norman group, so usability group from like human-computer interactions, there is also this limit of 10 seconds when users totally loses the focus and start like opening new tabs in the browser. But we'll focus on the middle one. So we got to a point that we can figure out what is the audio file that we should be looking into, and we should be recognizing. So we got the first point. We got the endpointing. So now we can get to the feature extraction. So now we can try to figure out what's inside this audio file, or what's inside this waveform, and try to find some actual words, let's say. So we go to the extract some voice features. What we'll be doing is we will kind of try to figure out what letters has been said. It's kind of letters, because when it comes to spoken word, there's no concept of letters. It's slightly different. I will get to that. In the minute. So when it comes to spoken alphabet, there are so-called phonemes, so phonetic units. And this is something we will be looking after. So we don't have, as we have written English and we have written Polish, for example, we have different letters which constitute for the whole alphabet. And similarly to spoken language, the difference is that in English alphabet we have 24 letters, while in English phonemic alphabet, so audio alphabet, we have about 44 phonemes, which altogether builds an English language. So, if we imagine that that's a sampled audio form, let's say that's exactly the same as it was before, saying me hello, for example. We need to find all those waves that are combined to create this form. So it's like playing a piano or playing a guitar. When you play a piano and you have a chord which is C major, for example, it is combined from multiple sounds like C, E, and G, and you have to figure out all those three separately to know that it's a C. It's a C major. It's something similar will be happening here. So the most basic tooling for that is Fourier transformation. So what we'll be doing is, if that's our signal, if that's our waveform, it is combined from multiple multiple waveforms, from multiple smaller sounds, and we will be trying to figure it out one by another. And Fourier transformation allows us to kind of calculate how much energy is being contained in the each one of those waves. And when we are speaking, for example, in English, each and every phoneme can be distinguished by the amount of energy that is being spoken and the amount of energy emitting kind of from our vocal tracks. So we can distinguish all the smallest sound, and then we can go on and map it on the whole words, more or less, simplifying it a bit at the moment. The thing is that when we do speak, as I do now, the audio is a constant flow of energy. So what we have to do is we have to cut those bits into as small pieces so we can try to distinguish them one by another. Based on some researches, we have found that a single phoneme is about between 10 and 25 milliseconds, depending how quickly somebody speaks or how slowly somebody speaks. So we can imagine that this whole waveform, or me saying hello, can be a spectrogram with a lot of small samples, like this one, each of 20 milliseconds, that is a sampled wave and contains the information how much energy is related to each and the other phoneme. And this is this feature vector. So we got all those features, so all those small samples, knowing how much energy is related to each of the sample. And then we can go to the next step. We can go to the actual recognition. So we have the waveform decomposed into smallest bits and pieces, and now we can try to figure it out what sample stands to what phoneme, and then get the information what has been spoken. So we can get actual recognition. There are kind of two approaches to that. One of this is a classical statistics-based method, based totally on the probability. I will get through that one. And there's another one which is pretty much implemented in Google Duplex, and it's based on some research papers that Google Brains team did back on last more or less 3 years, which includes some deep neural networks. But no matter which approach is being taken, the baseline or the basics of working through the audio files is pretty much the same. So I'll start with the classic one. This method is pretty old. Like one of the best book about voice user interfaces is coming from more or less early 2000s, and it is still valid, and still most of the recognizer is based on that. That's the starting point. So you can see that not much has changed in the whole concept of speech recognition throughout the years. Mostly our computers got much faster, and we can do certain things much faster. So when it comes to recognition, we have three things to look into. First of all, we have something called acoustic model. So we can represent a relationship between an audio signal and the actual phonemes or other linguistic units. Then we have a pronunciation dictionary, where there is a mapping how different words are pronounced. As you know, there are different ways of saying different words. I will get to that later. And then you have the actual language model, which tells you what is the chance that certain words will appear more frequently than the other. And that's exactly, for example, what is used in the spell checks and in all of the keyboard, the mobile devices keyboard. So the acoustic model. So we have a model that contains a relationship between the audio signal and the phonemes. So some linguistic units that makes up the speech. And phoneme is any distinct unit sound in a specified language. So that we can distinguish one word from another, for example, P, B, D, and T, as in English words like pat and pud and bud and so on. And so, as you can see, there are some very subtle nuances, and that's why there are more than 40 phonemes in English compared to just 20 letters. And there are languages that have like 70-something phonemes, which makes it much more complicated. There are multiple alphabets, like International Phonetic Alphabet, for example, is one example. And for example, we can have a phoneme K, which is in a word cat or in a word back. And it goes also, for example, for kit and skit and skill, but then if you're a native English speaker, you can see that there are some subtle nuances between, for example, K as spoken in kit and K as spoken in skill, which is the same phoneme, but slightly differently verbalized. And that makes one of the big problems, and for the classical speech recognition, that it makes it very language dependent. There are some trials to bypass that, and that's exactly what Google is doing. but in general, this is exactly the point where it's becoming language dependent. So these alphabets are for each and every language, and that's why, for example, we had a speech recognition first only for English, like native English, because when somebody did not speak perfect English, then they had some problems with recognition, and then different languages come over and so on and so forth. So if we take our audio file of me saying hello, and look at each and every slice of the audio unit, so each and every 20 milliseconds bit, we can try to figure out which phoneme has been set, depending on the amount of the energy that has been revealed. So we can imagine that throughout the sampled waveform, we might have said something like hello, because that's what it suggests. But this is never that precise, because we have some background noises. We don't say the perfect pronunciation, so there is a fair chance that what we figured out as a pure audio also will go for like a, which is still a valid sound, but that's not probably what we were what we've been saying. So the first step is that, based on the acoustic model, we have some vague idea what phonemes has been said, and also depending on how quickly or how fast somebody is speaking, we can get the same phoneme, for example, for longer or shorter amount of time. It's like when you say, Alexa, play the next song, and you say, Alexa, play the next song. That's different audio form. So that's the different amount of phonemes being figured out. So that's the first challenge, but that's quite easy to bypass. Now we have to try to match the phonemes that we think are there with the actual word. So we get a pronunciation dictionary. So we have, again, a complete list of words for the certain language, like British English. And then for those 90-something thousand words, we have an exact pronunciation, how things are being pronounced in multiple ways. So we have like a word and a pronunciation derived with one of the phonetic alphabets. And as you can see, there are a lot of words that can be pronounced in an all different way. So having a phonetic dictionary, we pretty much know the exact word, how things are being spoken, and what we need just to do is try to reverse. We don't have a word, but we have some idea what phonemes might have been said, and that's where the probability kicks in. So how most recognizers work at the moment is that we can imagine that the phonemes, so what we figure out, what we heard from the audio file, is a kind of an observation, and the word we are trying to figure out is the state which is unknown, and that's how it actually works. So if we can simplify that to a feasible example, we can imagine that we don't have 96,000 of states as the words, but we have two states, that somebody is either healthy or is having a fever. That's, for example, me today. And then we have a bunch of an observation. We can see weather, how weather is looking. So it's like normal weather. It's cold, and it's dizzy. So that's our word, as we say, as we see. So if in our speech recognition word, the states are the words, and the observations are different phonemes that can be spoken. And based on the language model, we can have different set of probabilities. So we can have a start probability. So there is a fair chance that in 6 out of 10 cases I'm rather healthy, or I have a fever. There's a 40% chance. And given that I am healthy today, there is a fair chance that I'll be healthy tomorrow. So we have the transition probability, and we have emission probability. So if the weather is normal and I am healthy, there is 50% chance that I will stay healthy. And given this model, we can try to figure out what is the chance that if the observation for the weather will be normal, cold, and dizzy, so it will be normal today, cold tomorrow, and it will be raining on the third day, what is the probability that I will be either healthy or have a fever? And that's called hidden Markov model. So we can graph it, because everything is well known, and we can walk through it one by another. And it's called the Viterbi path, so a way to figure out the most likely sequence. So if we start as a starting point, we can be either healthy or having a fever. So there's a 60% chance of me being healthy, and as the weather is normal, it's a multiplication, so it's a probability. There's a 30 chance I would say stay healthy given that observation, and same with the fever. And then we can go on. The next day it's being cold, so we go from healthy and fever. There's the possibility changes, and so on and so forth through all the observations. So after the third day, I rather have fever if that's just cold and dizzy. And similarly, it works for the spoken language, but the probability graph is much bigger. Based on statistics, we can say that, for example, the most popular vowel in English language, for example, is A, and then there's E. And if somebody starts saying hello, so they said H, E, and L, there's a fair chance that they will continue with another L, and that the probability of saying hell X, Y, Z is much smaller than saying hello. And that's where all the tongue twisters are coming from. That's why it is harder and much less probable to say how much would chak chak if it would chak would in English than any other sentence. And similarly in Polish, that makes the przebrzeszenie książ brzmi w trzcinie very hard to say, because the sequence of phonemes that we are trying to emit is very improbable, and that's not what our vocal tracts are used to do. So based on that, we can have some kind of idea what word has been said. We figure out a certain probability of different phonemes, and those phonemes can, with a certain probability, constitute to one of the other word. And this is exactly the point where, in the past 10 years, the speech recognition was doing its innovation. The computer were getting faster. We could have worked much easier through the whole language model. Back in the times, like 10 years ago, we could have only say kind of a grammar-based language model. So we could have said that we believe that in this part of the dialogue, somebody will say those two words, and that's what we are betting on. Now, as the computer got much faster, we can scan through the whole language and try to figure out the word. So that brings us to the third part. So we have the whole statistic of the language, which is a probability distribution of a sequence of words, and that's how most of the speech recognition engines at the moment work. We know that if we have, as in our example, a word hello and a word aloo and whatever, in English language, we rather say hello. And the most classic example in speech recognition is that, from phonemes perspective, saying recognition speech and reckon a bitch is exactly the same. And they make totally different words. And based on the statistic language model, we say that recognition speech is rather a more probable sequence of words than whatever else. And that's exactly how autocorrects on most mobile phones works. They have this idea that it's statistically more probable that you've written this word than the other. And then we can enhance it with some grammar. So whenever you add something to the dictionary, you try to boost a single word for it to be more probable in the recognition process. And exactly in the same way we can do with speech. Okay, and that's pretty much the statistical part. What Google has recently done, and they announced it as a Google Duplex on the Google I/O, and it is based on some research papers from Google Brain teams from last 3 years, more or less, is try to bypass the whole language thing whatsoever. Because all this probability-based stuff makes speech recognition language dependent, because those probabilities differ from language to language, and makes it very expensive. We have to figure out and try to codify the whole language, which can never be done exactly, because the language is something which is alive and evolving, and it changes from year to year. And if there will be a chance for us to show the exact audio signal directly to the neural network and let it figure it out for itself how it's going, so that's exactly what Google is trying to do at the moment. In the most simplistic approach, we have a kind of a recurrent neural network. Why it should be recurrent? Well, Google is done on totally bidirectional network, but recurrent because based on the previous guess, or based on the previous example, we can boost or lower the probability of the next words that will be figured out. So we have a small audio slide, and then we feed it up to the neural network, and there's a different likelihood of saying different words. So if we get back to our hello example, what we will be dealing with will be the actual letters and saying hello in a more or less different way than the phonemes, which we will have to go through the whole statistic model to figure out what is being said. Okay, and that brings us to the whole recognition part. So we can get fairly easily and fairly with a good correctness to the point that we have transcript the audio file to a word, to a single word. What Google people are saying that this statistical approach to speech recognition can give you more or less 95% correctness, which is pretty good example, especially if you can put it in a certain domain and you say that, for example, you're doing speech recognition only for insurance or for banking, and that you know that somebody is, for example, calling for a bank, and that the vocabulary will go in a certain direction connected with finance, that you can get really good recognition rates. But what you can do with the neural networks, you can boost it for to 98, 99%, and that makes a huge difference in terms how people are perceiving the quality and the results of what is being recognized. But recognize the actual words is only a halfway or part of the work. We still have two things to do. We have to give those words a meaning, so do some kind of natural language understanding. So put the words in a context, know what they mean, build a kind of an abstraction on those words, and then design a dialogue. So build back and forth discussion that is possible, designed for this discussion. And then again, for the past 10 years, most of the innovation or most of the figuring out how to make those speech recognition better was related to a way how easily or how good we are in spotting up some of the keywords that gives the meaning to the recognized words, and how we've built the actual dialogue. So how natural was the dialogue? And there has been a lot of cheating in that base, where things were totally grammar-based and predefined dialogue, but it has been built in such a way that gives a perception that, yes, this computer is kind of natural and it works like easily and nearly out of the box. So we can try to bring it all together. What we've seen so far is a kind of an argument formulated by one of the computer scientists, John Searle, about a Chinese room. That a properly programmed computer with the right inputs and the right outputs could have been mined exactly in the same sense as human being having a mind. So you can imagine a situation when somebody is sitting in the room and you hand over to them some Chinese characters written on a piece of paper. The person in the room knows no Chinese whatsoever, but they have a transcription book and they can look up the words, the signs in the book, and write down the answer and hand over the card to you. So externally, you can have an idea that a person inside the room knows Chinese. But what they did is just they transcribed one sign to another without even understanding what the words were about. And that's where we got to the point with most of the speech recognition as we are at the moment. So we can recognize the words, but giving those words a meaning make it much harder for the computer. And figuring out those two last bits, so how to build an understanding and how to build a dialogue, is much harder than actual recognition. What we can do more and what we can do next is we can either invest a lot with understanding what has been transcribed from the spoken language, or we can kind of bypass the fourth step and focus more on the building a dialogue in a way that we can pretend we understand, but we don't do that ideally. This is called designing for incidental users, because when you build any kind of voice interface, you get people that are totally passive in terms of ability to interact with the system. So they have no prerequisite knowledge how it should be operating. They have no idea where to look for any help. And that's, for example, the reason why Google and his assistant at the moment, when you say, OK, Google, it pops up a graphical interface and has a kind of a prompt coming from Google. How can I help you? And then there is a little bit shadowed, what can you do? So I can either say, what can you do? Or the Google suggests me how to further explore the dialogue and how to further explore the application. Because that's the hard part in the voice, and in the voice recognition and building the whole natural dialogue. Dan Norman, another usability guy, said at some point that the proper behavior comes from carefully crafted design, not through instructions, manuals, and warnings. And we as a computer scientist or computer programmers know that pretty well, that it should be done in a way that no manuals are needed whatsoever. The thing is that when we get to a point of purely voice interactions, it gets much harder, and there is a lot of chances of going in the wrong direction, branching or betting on the wrong, branching or betting on the wrong branch. On one hand, it opens a lot of possibilities, but on the other, it makes things much harder. So that's pretty much what I prepared for you today. That's something what I wanted to. What I want to share. If you would like to drill down a bit in terms of the actual voice user interfaces, there are some links and books that are worth reading, starting from designing the process or designing the actual voice user interface to how different bits and pieces actually work, how Google is approaching that, or how other statistical-based research are being done. So if you have any questions, I'm happy to answer. If you want just to show for lunch, I fully understand it. Thank you very much.